Thank you, Zichao, for the generous introduction. And I wanted to just start by showing this beautiful photo of my students who, like Cynthia, are contributing to making our world beautiful, and that we dedicate some of our time, not all of our time, to do something good. And I really enjoyed the last talk, but also I'm inspired by the dedication that Lori and Bengt have put into creating the Molecular Frontiers Foundation that is dedicated to emerging scholars everywhere. And it's always a pleasure to participate in these talks or in these occasions. So this is one of my students. I believe it's Wuchol, but I'm not sure. There are 3 of them that went to the Death Valley to test the water harvesting device, our latest water harvester. I will talk more about that, but I do admire them, and they inspire me every day because they really went out of their way to be in that environment, very harsh environment, to test the harvester. This is a beautiful photo of Death Valley at night, one of my favorite places in the world. Okay, I don't like the flicking of the screen, but I have to live with it. Okay, so our world, although beautiful, but we have a lot of problems. We have problems in energy, we have problems in climate, we have problems with food, water, health, and this is just a few. I mean, there is greed and war and other problems, but I won't talk about those. I want to just say that I think that many of these problems can be solved by creating new materials. And before everybody jumps on me for creating new materials and potentially new problems that come with materials, I think that advancement of civilization has always relied on creating new materials, and it is really society's responsibility to make sure that whatever we create in technology, it will always have good things and bad things, but we need to anticipate the bad things and head them off. That's the nature of I think, progress. So just as an exercise for the emerging scholars here, I want to just ask this question: what do you think are the most important materials created by humanity and used today, until today? These are materials where economic ecosystems have been built around them, and we use them every day. I have a list of about a dozen of these. I want you to make a mental list and see, okay, somebody volunteering. Metals, right. Without metals, we will not have alloys and things that we can use for flight. But my list has wood, okay, and concrete. In fact, if you go to many countries, they're very proud of having very tall buildings. That's just a sign of progress. In the UAE, for example, you have one of the highest, or maybe the highest now, building. Metals has been mentioned. Glass, we can stay inside and still see outside. Silicon, without it, of course, no communication, no computers. Petroleum, without it, our quality of life would decline. Plastics have made things accessible to many. And pharmaceuticals improved our life expectancy. Fabric, the whole world centers around fabrics and fashion, and paper. And one thing that is true about all these materials is that the more we are able to fashion them on a minute level or tinier and tinier level, the more useful they are, and the more, I would say, have really advanced and made our lives easier. So, but these materials are not, they will continue to be important, but they're not going to solve those problems that I just talked about. We need to be able, I would say, to fashion materials on the molecular atomic level, and to do so nearly at will. We need to be able to design. And so chemists, someone, I think it may have been Harry Gray, who said chemists will save the world. because they can do things on the atomic level. And that's true. I mean, chemists have spent the last 100 years learning how to stitch atoms together to make molecules. And some of these molecules end up being pharmaceuticals that make our life much better. Now, I want to talk to you today about linking molecules together to make materials, which is something that we haven't done so far, well, or up to the work that we have done. We have not done. And in fact, if you were to make an extended material, when I was a student, you basically took your starting materials, you grinded them, and heat them up to 1,000 degrees, and you got what thermodynamics gave you. You made metal oxide, metal nitrides, metal sulfides that way. You made inorganic materials. They're useful, but there was no design. There was no rational design. It was not, to me, it was not satisfying. And in fact, when I was a student, this is a statement that appeared in Nature, was written in an article that was written by John Maddox. And he writes, one of the continuing scandals in the physical sciences that it remains in general impossible to predict the structure of even the simplest crystalline solids from a knowledge of their chemical composition. That just says we didn't know what we were doing. And in fact, as a student, I was engaged in this kind of research. We used to call it in those days shake and bake. Okay, but now shake and bake has a different meaning in society. But in those days, it just meant that you didn't know what you were doing. You were just cooking in the lab. Well, there's a reason for that, is that if you really want to stitch molecules together in a rational way, in a well-defined way, you fell into a problem that I call the crystallization problem. And everybody here will not deny, especially the people who are as old as I am and maybe older, will not deny the fact that we all thought that it can't be done. Because once you start stitching things together, especially through strong bonds, the belief was, and still you can find many examples, is that you will not make well-defined material. You're not going to crystallize your material. And if you can't crystallize your material, you're not going to know what you made, because crystals are the god of chemists. I mean, every chemist spends the majority of their time crystallizing their material because we know how to characterize them using X-ray diffraction on the atomic and molecular level. So once you know how to characterize your material, you can definitely improve it and use it as a starting point. So there are many examples like dry ice. Dry ice is our molecules linked by weak bonds. And it's easy to crystallize. Water, we've been talking about water. Water is easy to crystallize because the molecules are linked through weak interactions. Even things that we call coordination networks or coordination polymers, where you have a neutral linker and a metal ion, that's weak interaction. That interaction is about 3 times as strong as a hydrogen bond, still not as strong as a covalent bond or a strong metal ion charged ligand bond. So these are, that's what was there in 1988 when I was a student. The thing that we have been addressing is how do we go to stronger bonds, okay? So for example, charged linker metal bonds, that's much stronger than these neutral linker metal bonds. And covalent bonds, the ultimate strong bonds, especially for organic compounds. That is where we are. We've developed metal organic frameworks. They are linked from metal ion and charged linkers. Those are basically the stitching. This is the linkage. And we develop covalent organic frameworks where the linkage is strong covalent bonds like boron, oxygen, carbon, nitrogen, and so on. That's, I would say, the supramolecular chemistry was defined by Jean-Marie Lehn as the chemistry of the weak bond. I would say reticular chemistry is the chemistry of the strong bond. That's what's new here, is that we are able to crystallize systems by stitching molecules together by strong bonds, and the chemistry works. So once once the chemistry start working, you start thinking about things that were impossible to think about before. For example, if I take a grain of sand, okay, it has a surface area of no more than 1 meter square per gram, okay? But if I take that grain of sand and I expose every atom in that grain to an incoming hydrogen molecule or an incoming gas, meaning if I make every atom in the grain of sand an adsorptive site, then I would have made a porous material. Okay? That's, in reticular chemistry, that's basically what you're doing. You're taking building units, like in this Usher drawing, and you're taking, at least in MOFs, you're taking metal oxide units and linking them by organic units to make open structures. And everything in that structure becomes an adsorptive site because they are encompassed by porosity. So I always say there's nothing new under the sun, or this is actually from the Bible, nothing new under the sun. So there were examples in the literature called coordination polymers, where you take neutral linkers like this dinitrile, link it up with copper-1 to make these extended structures, the so-called coordination polymers. So this structure has nitrate that fills the pore and balances the charge on the framework. These are extended. If you were a molecule, you would see an infinite arrangement of these things across the entire crystal. And the same thing was illustrated also in 1986 for the same kind of network, but now this diimine dinitrile, same chemistry, and the same thing was also repeated in 1989, but now with a tetranitrile, okay? And all of these are based on diamond structures. They're all based on copper-1 linking nitrile neutral linkers. And they all have this openness into which ions can balance the charge. And since that time, there's been hundreds of these made, or around that time, hundreds of these made. And so when I joined Arizona State University as an assistant professor, because none of the other universities like Berkeley and Columbia wanted to hire me because Harry Gray, you weren't there when I interviewed. Otherwise, I probably would have gotten the job. But nobody believed that you can stitch molecules together to make crystalline materials. And so, but Arizona State University took a risk on me, and I appreciate that. And the problem is that we started working with these. It was very attractive. I mean, you have an organic linker, a metal ion, can stitch these things together, and potentially, if I can use this porosity, it would be amazing. I can fashion the pores. I could do many things that organic chemists can do with linkers and inorganic chemists do with. But it turns out they were completely useless. They were just nice sculptures, but they didn't do anything. Whenever you try to exchange the ions or exploit the porosity, they collapsed. They were not designable because, as you know, copper-1 could be tetrahedral or it could be trigonal. So you couldn't quite predict. And definitely they were not chemically stable. They were made from weak bonds. And so, in fact, some of those dissolve when you put them in organic solvents. So that was the problem that we faced when I was assistant professor. And so, trained as an inorganic chemist, I immediately realized that you could take metal ions, and now, instead of neutral linkers, you can have charged linkers. And if you choose carboxylates, not only can you strengthen that interaction, in fact, a cobalt 2+ carboxylate bond is a very strong bond, almost as strong as some of the covalent, organic covalent bonds. But we illustrated that you could take, for the first time, that you can take an anionic linker, organic linker, and link it up with cobalt and make a crystal. This was the first illustration. I would say this was the beginning of what, in those days, I called metal organic frameworks, and now people call MOFs. I just want to emphasize, especially to those who are interested in history, is that it was taken as an article of faith in chemistry, or in the chemistry community, that such strongly bonded structure could not be crystallized. And in fact, some people actually wrote statements to that effect. Well, I was the kind of person that if somebody said it couldn't be done, I always pursued that. And well, I pursued that, but I also handed over to my students, and they get it done. So, okay, so we're able to crystallize them, but now this is how the chemistry works. You take a metal ion, you have an organic linker, in this case, terephthalic acid, and you put in DMF, in this case with some amine, and you crystallize the material. The discovery here was the very, very initial way we discovered crystallinity or how to crystallize them was that DMF, when heated, decomposes to make amine. And that amine then turns around and deprotonates the acid. And if you can control that, the rate of deprotonation, you can control this reaction, the crystallinity. And that was really what opens up this field. And it turns out that DMF, until today, is part of the cocktail of making MOFs. DMF or some other, like NMP or diethylformamide, very similar. So this is what we made. And this is called in inorganic chemistry a paddle wheel. It's linked by organics. And when you make this, there are DMF molecules filling up the pores. And the big question was, could we remove the DMF and will the structures remain open and rigid? And the answer to that came from measuring a gas adsorption isotherm, which has to be done at 77 Kelvin. You evacuate the pores and you expose them to tiny amounts of nitrogen. You see the nitrogen going in the dark circles, coming out in the open circles. It's very reversible. It has a type 1 isotherm. And you can do this also with CO2 just to show that, in fact, that this structure can remain open in the absence of anything in the pores. So at this point, nobody noticed this paper except the 3 referees that reviewed this paper, and I got very, very positive reviews. In fact, maybe the very first time and the last time that I got 3 very positive reviews on a paper. We use the same method. Now you see we have gotten to the basically the cocktail that always produces crystalline MOFs. You see DEF or DMF, but DEF heated to produce the amines that go in and deprotonate slowly to crystallize the material. Then we made this one. This is MOF5. This is a metal. This is zinc oxide units. Inorganic chemists call this core the basic zinc acetate structure, which has been known since Pauling started making, or Bragg solved the first crystal structures of these basic zinc acetate structures. And you see here it has an openness, that the yellow ball indicates a space within which things can be incorporated, like for hydrogen storage or carbon capture. The structure looks like this. It's extended. It's infinitely extended. And the isotherm is shown here. Type 1 isotherm, showing that, in fact, it remains open in the absence of guests, and the pore volume was 61% of the entire crystal, 61% by volume. And the Langmuir surface area that you get from these nitrogen adsorption isotherms at the time, we calculated to be 2,900 meters square per gram. That, when we reported this, everybody paid attention because this broke all records of porosity that preceded MOFs with zeolites and porous carbon and other materials. Much later, there was a nice article written in CNN News about commercialization of MOFs, and they had interviewed one of my very early collaborators at BASF, and in this article, I learned for the first time that he thought that when we reported the surface area of MOF5, that the number was so unbelievably high, I thought it had to be a misprint. And that started my collaboration with BASF. is that they didn't really believe that that surface area is real. They thought that we missed a decimal or whatever. And this is a picture of them scaling, and I'll show another one scaling the MOFs at multi-ton quantities. So my talk is divided, I neglected to mention that my talk is divided roughly, half of it is about materials and how we were successful in making them, crystallizing them. And the other half is how that is an extremely powerful materials because they are crystalline to harvest water from desert air. Okay, so that's what I wanted to say. But once you know the conditions under which this basic zinc acetate corner or junction results, then you could use the same reaction conditions to use linkers that are functionalized or expanded. And therefore, now you could make materials for the first time where the pores could be functionalized and fashioned for a specific application, or they could be expanded to be able to bind progressively larger and larger molecules. So I said that every atom in these structures is an adsorptive site, but I didn't show you evidence of that. So now I'm going to show you evidence with an almost impossible experiment, which was to take this MOF5 structure. Remember, I said 61% of the structure is just empty space, and you evacuate it, you put it in a capillary for X-ray diffraction, you cool it down to 30 Kelvin. Almost every crystal you know will not withstand, will not maintain its monocrystallinity, will be rendered useless in X-ray if you cool it down to 30 Kelvin, because they will crack and they will lose their monocrystallinity, especially porous materials. And so this was a very first time success to analyze the structure just where the pores are empty, and now you have just the framework. And you see here, for the inorganic chemist, this is 90% ellipsoids. This is a crystal structure, very well behaved, and proves beyond doubt that your structure is open and does not collapse in the absence of stuffing or of guests. But then what this student did, which was really a great experiment, was to dose the crystal with very tiny amounts of argon and in another experiment, dinitrogen. And the object here was we wanted to identify what are the adsorptive sites. Where does nitrogen bind? Where does argon bind when it's introduced in the structure? And it turns out, I'm showing the results here for argon, but for nitrogen it's very similar. Argon is in yellow, and it turns out that everything you look at in the metal oxide unit is actually an adsorptive site. All of these bind argon, as well as the six-membered rings and the edges of the six-membered rings. So that's where every atom in the structure is an adsorptive site. You're making maximal use of your material, and that's why they have extremely high surface area. The more adsorptive sites you have, the higher the surface area it is, because the surface area is coming from the amount of nitrogen that you have measured in the gas adsorption isotherm. So once we have identified the adsorptive sites, now my students very quickly can go to the lab and link longer linkers that have more and more exposed edges and faces, and with that metal oxide unit. And now you have a material that has a surface area of 6,400 meters square per gram, okay? It's unimaginable that you could make a material that has such a high surface area. 1 gram of this material, if I was to unravel it, it would cover an entire football field. That's what that porosity is equivalent to. 1 gram, which is no more than this, could cover an entire football field. That's the amount of space that is available for gas molecules to go in. And so, like I said, now the chemistry works. We have figured out the cocktail, the conditions under which to make things crystalline. You can deploy different metal oxide units, covering almost every metal in the periodic table, and we can use simple organic building units to link up the metals, and also long linkers and exotic-looking linkers, chiral linkers, and so on. You name it, everything. Everything you can put carboxylate on could be made into a MOF. And just for a dramatic effect, you could progressively expand the pores so that now you can go from pores that are only 0.1 nanometer to pores that are 10 nanometers. And you can do this incrementally. And if you like, you can also study the inclusion of proteins and enzymes inside the pores. So what I'm trying to say is that if you think it, you can make it, because the chemistry works. And that's really what Harry Gray was referring to, is that the power of being able to manipulate things on the atomic and molecular level will always generate materials that will solve many problems that we are facing, as I will show you shortly. But basically, this is a periodic table of reticular chemistry where all you have to do is identify the molecule and describe its geometry, and then link them up, and we know exactly what's going to come out, okay? And we are right most of the time, but not all of the time. 80% of the structures that result are highly symmetric structures, so they're very easy to identify. Among the millions of structures that are possible, only 3 or 4 dozen that are highly symmetric result. And so if you want something that's not as symmetric, you have to use less symmetric building units, and that will give you structures that are not as symmetric. So you have all kinds of shapes that result in different structures. And some of these blocks, for the emerging scholars in the audience, are still open and available for you to discover, okay? There's more blocks here, you see more blocks. But what the point I'm trying to make here is that if you just zoom in on one block, I don't know if you can see yeah, you can see. On one block, you see that I could spend a lifetime studying the chemistry of this framework. Why? Because the metal oxide units could be varied among many metals. The organic linkers could be varied in size, shape, functionality. So there's a lot you can do in just one block. And that's why this chemistry is now being practiced in over 100 countries worldwide. So we have been able to make materials by stitching molecules together to make extended structures that are porous and that are crystalline. You can see here in this movie, you have crystals with sharp edges, faces, and you can characterize them by single crystal X-ray and know exactly what you have and how they're connected and all these structural parameters. They're very open. And the idea was that gases that fill very large volume could be compacted within the pores without having to use high pressure or very low temperature. So that now you can store gases in an efficient way. So that gas, because of the adsorptive sites that are encompassed by these structures, basically gas molecules touch the surface or bind to the surface just like bees on a honeycomb. And that's why you can compact them into smaller space, foregoing the need for high pressure and low temperature. So as I said, I have been collaborating with BASF for 17 years. And through this time, we worked out all the scale up of many MOFs in multi-ton quantities. And now MOFs are being made in water, not DMF. That's another great thing about chemists, is that when we discover a material, it might be under the most unattractive conditions, but once we dig into the chemistry, we can transfer the chemistry into water, and that's true of many, many MOFs that I will be talking about, especially for water harvesting, would be preparation is in water. So this is one of the MOFs, and you can see just a nice, well-behaved white powder. In this case, it's zinc MOF, so it's white powder. But you can have copper MOFs, and the BASF shapes them in different shapes for different applications concerning gas storage. Okay, so that's MOFs. MOFs basically took inorganic chemistry, metal complexes, and organic chemistry, and combined those two fields into one. that I call reticular chemistry, where you're taking advantage of all that knowledge that we have of organic compounds and all the knowledge we have of metal complexes, and to make new structures that encompass space within which one can control matter even further. So that's MOFs. For COFs, somebody said they didn't care for Roald Hoffman's class. They hated chemistry. Roald Hoffman was one of my idols when I was a student because he wrote articles that you can read and understand, especially on molecular orbital theory. So I enjoyed reading his books. But he wrote, organic chemists are masterful at exercising control in zero dimension. One subculture of organic chemists has learned to exercise control in one dimension. These are polymer chemists, the chain builders. But in 2 or 3 dimensions, it is a synthetic wasteland. This was back in 1993 when I studied as assistant professor. What he's saying is that covalent organic structures that are 2D or 3D in crystalline forms are unknown. It was wide open. And I know why, because when I ask my students to link organic molecules together to make by covalent bonds, this is the kind of X-ray powder diffraction that they get. They get this big hump. And students being smart, they don't want to work on a project like this. They want to work on a project that works so that they can write a paper and graduate and start their life. So you go to undergrads, because we can sacrifice the undergrads. So this Annabelle was the undergrad that made this work. And she zoomed in on this molecular reaction. You see here this boronic acid. This is known. You can dehydrate boronic acid and make this triboroxine anhydride. This is a flat molecule. This is a planar molecule because there is a weak CHO interaction here, a weak hydrogen bond that makes the molecule planar. And from a reticular chemist point of view, I can take those building units and imagine that I'm reticulating them, and I can calculate the powder diffraction for them. But of course, you go to the lab. She went to the lab and she tried it. Of course, she got that hump. But after many different conditions, and what you're doing here, you're not really working in the dark. What you're doing is you're trying to balance the rate of the reaction with the expectation that you need a rate where the molecules can have that microscopic reversibility, that linkage. You can form the linkages and break them. Okay, that's microscopic reversibility. If you don't have that, you're not going to crystallize your material, because if you just bind them together and they cannot break during crystallization, you're not going to make crystals. They will be full of faults and defects. So these are the conditions under which she found that they work, because we realized that water is a byproduct, and these were done in sealed tubes. And so if you control the pressure of water in the sealed tube, you control also the reversibility of the reaction and the microscopic reversibility of the reaction. That's boom, that was the key to making these in crystalline form. So it turns out this is the kind of recipe that people use now to make many, many COFs, not just from this linkage, but many other linkages. So that hump you see here turned into this sharp X-ray powder diffraction, which matches what we anticipated. And COFs, unlike MOFs, because the building units don't change during the reaction, they remain what they are, but you're just making bonds between them, you can always give excellent guesses to what you're going to make. In fact, they may be the first class of materials that were made truly by design. So I want to get to water harvesting. This is the last COF slide that I want to show. And I just want to show you that you can make COFs from extremely, what organic chemists have taught us are irreversible linkages, irreversible bonds that you can't, meaning you can't crystallize these, but you can. Every bond is reversible. You just have to find the right conditions under which to make them reversible. So these are the conditions under which you make these olefinic linkages reversible, and therefore you crystallize this material. Why do we want olefins? Because we want backbones that are extremely stable so that we can use them for water harvesting or carbon capture, and they can stay in a plant, in a power plant, for many years before you have to replenish the material. You need that. You need those strong bonds so that they don't hydrolyze, they don't decompose under those chemical harsh conditions. This is how crystalline the material is, and it's extremely stable in 12 molar HCl, saturated KOH, even corrosive environment like N-butyllithium. Why? Because it's made from carbon-carbon bonds, very, very stable bonds. So, COFs based on these linkages have been made by our group and others. You can see here many, many linkages that organic chemists thought are irreversible. Now we can make them reversible and crystallize them. Okay? The ultimate thing for me is to show that, in fact, these extended structures could be made as single crystals so that you can do single crystal X-ray diffraction, which what organic chemists use to characterize their compounds. And there we have been successful, as you see here, by adding aniline to compete with in this imine reaction, slow down the imine exchange in the COF synthesis, you can control the nucleation and make very large crystals that are amenable to single crystal X-ray diffraction. What I'm trying to say is that we have taken inorganic and organic to make MOFs as crystals, and we have taken organic molecules and stitched them together to make single crystals of COFs. So we are on the same, I would say, level as the molecular chemistry that has been now practiced for 100 years. But now we've translated this. We have propelled inorganic chemistry and organic chemistry into the 2D infinite direction and 3D infinite dimension. So that's all new chemistry. And that's why these have been important in harnessing the power of molecules like hydrogen. So we've used them for hydrogen storage, for methane storage, for carbon capture, and as I will describe today, for water harvesting. And in my lab, we are able to also not just make the materials, but take them all the way to prototypes and work with, in this case, with BASF to show that in fact a natural gas tank works and hydrogen storage works in automobiles, and CO2 capture can work on and show that in fact you can capture CO2 from air and flue gas. These things I won't describe today, but I want to focus on the clean water. The fact that we can take molecules, make materials out of them, engineer prototypes, gives us a lot of ability to reach society. So, okay, so in the last, let's say 10 or so minutes, I want to describe our work on water harvesting. This map shows the water-stressed regions of the world. You see there in red, these are water-stressed regions for most of the year. Our idea is, could we create a MOF that extracts water from low humidity? If I can do that, not only could I supply water to these Mediterranean regions or western of the US and other regions like in Australia or South Africa, but also that same material will work at higher humidity. So the key is, can we design a material that can take water at low humidity, meaning humidities of 10%, relative humidities of 10%, 20%. Okay, so if we can do that, then we could extract water from air anywhere in the world at any time of the year, regardless of the season. And so that was really the dream. If we could do that, we would have capitalized on an important resource that is completely recyclable. There's almost 13,000 cubic kilometers of water in the air at any one time. That's almost as much as we have in lakes and rivers on our planet. Okay, if I could serve each person on our planet 50 liters a day of water, I would have only used less than 0.01% of the water in the air. So this is a huge resource that is sitting there and could help solve our water problem. Now, for a humidified region where you have fog, like at the coast of Namibia, this desert beetle has figured out how to harvest water from fog. And I like this beetle because on its back it has ridges, and the ridges are hydrophobic and hydrophilic. It's really a grid of hydrophilic and hydrophobic that alternates and covers the back of this beetle. And this is a very, very important principle, I think, for harvesting water, is that water is attracted to the hydrophilic region. And then as the droplet grows, it needs to seep down to the front of the beetle so that the beetle can be hydrated. So what it does, now as the droplet gets large enough and now touching also the hydrophobic region, gets propelled down, and that's how it's regenerated. So you need this hydrophilic and hydrophobic to harvest water. Fog, of course, fog has been captured in these nets and so on. But again, all of these are humidified regions. But what about regions of the world where there's low humidity? Humidities of less than 50%, okay? That's very hard to do. And the reason for that is that if you look at this psychrometric chart, you have water vapor. I'm plotting water vapor in air in grams per cubic meter versus temperature. And so you get these humidity lines, 10%, 20% relative humidity, up to 100%. And then roughly I am coloring the humidified areas in green and the dehumidified areas in brown. Okay, so let's imagine, just to show you why it's so difficult to harvest water from low humidity air, is that let's imagine I'm in a city, Mediterranean city, where the temperature is 30 degrees Celsius and the humidity is 20%. For me to get that water out of that air, I need to cool the air down to the 100%, right? And down to 4 degrees Celsius. Okay, that's like refrigeration, and that's not very energy efficient. So the way the MOF would work is that the pores that I have been describing to you could be tailored to pluck out water from the air, concentrate it into the pores. And in a closed system, I would basically make a humidified atmosphere. Okay, so that water that's stored in the pores humidifies the box or wherever they are contained. And now to get the water out of there, I only need to cool down by a few degrees. Okay, so in essence, what I'm doing is I'm taking desert air and turning it into tropical air. That's really the principle by which the MOF works. So I wouldn't be telling you about this if we didn't have the MOFs in hand already, right? So we were studying CO2 capture, and CO2 capture you have separated from water. So we were studying also water harvesting, and this is the first MOF where it showed that in fact you could do this. Here's the uptake of water in that MOF. You see here that the amazing thing is that it's taking up water at around 20% relative humidity and doing so using this sharp knee behavior, which means that for me to take out this water, I only need to change the pressure by just a few, just by a few digits, basically, to allow or just to lower the pressure slightly to get the water out. But thermally, you can take the water out at 45 degrees. So having grown in the desert in Amman, Jordan, I knew that at night, the desert is cold, and during the day, it's very warm. So I thought, well, you can take this material, put it out at night, and it will take up water from air at night. And during the day, I put it in a box, close the box, and as the box heats up, I can harvest water because the temperature to take the water out is very low. Now, we all know zeolites take up water from low humidity, but you have to heat them up to 200, 300 degrees Celsius to get the water out because they're very hydrophilic. But here, you don't, because you have the organic units and the inorganic units, the hydrophilic and the hydrophobic, modulating how strongly the water is bound into the pores. Okay, so we tried then, we cycled the water in and out of the material, and you see here a very nice uptake and release up to 80 cycles here. But we also notice that after the very first cycle, we lose a little bit of capacity, okay? So something is remaining in the pore that doesn't come out, okay? Some water molecules are sticking in the pore. So this is where I would say being able to do this by crystal structures is very useful, is that we can take a crystal structure, both X-ray and neutron, to identify where the first water molecules are binding. And it turns out the very first water molecules are bound to the hydrophilic regions on the metal oxide units. And they make tetrahedral shapes, and as you add more water, they make cubic shapes. But that's basically, that is the amount of water that stays in the pores, doesn't come out. That's the seed onto which other water molecules will bind. And that's why you have that very nice cooperative behavior, what I call the sharp knee. If this material was not crystalline, you would not be able to get that sharp knee. Because if you have a distribution of those adsorptive sites, because your material is amorphous with many different adsorptive sites, you will get a shallow isotherm, and you will not get a very good, efficient material. Okay, so that MOF, we scaled up to kilogram quantities, and we did exactly what I would have done in the desert, is put one box inside another. The smaller box has the MOF in it. The outside box is closed during the day, and the vapor comes out and condenses on the sides. And this is what it looks like. Okay, it's just made from plexiglass. And this is the water that condenses on the walls of the larger box on the inside. And this is, you see here, the collected water. We collect about a cup of water per kilogram of MOF. Okay, it's not optimized, but it shows I can, in the Arizona desert, where the humidity in this case was 30%, I can collect water from the air and generate a cup of water. If I want 2 cups of water, I could use 2 kilos. I think the powerful thing here is that you're generating water without energy input aside from ambient sunlight. I'm not electrifying this at all. But if I want more water with less MOF, I just electrify the system, and the fact that I don't need to heat up the material too high means that I can get it an efficient uptake. So this is a student who surprised me with drinking the water.
2, 3, action.
Cheers. Nice.
Eugene is alive because we tested the water for metals and organics. Absolutely, it's ultra pure. It's distilled water. It doesn't taste very, very good. You need to mineralize it to make it taste good, as was mentioned earlier. But remember, the MOF itself is just also a filter for water, because only water can enter, because the pore size is about right for water molecules to pass through, and no hydrocarbons or other things that may be in the air. And this is another advantage to reticular chemistry, is that the MOF that I just showed you is a zirconium MOF. Now we can make an aluminum MOF and avoid the expense of zirconium. Aluminum is dirt cheap. And we have a linker like this. It's not widely available, but that's because there's no demand for it. We are the only demand for this material. And you make a MOF. And if your eye is inside the pore, you'll see this. You'll see the hydrophilic pocket and a hydrophobic pocket. This is the NH on this side, NH on that side. Perfect for water seeding. Water goes in here, and it has a hydrogen bond donor and acceptor. So hydrophilic, hydrophobic, hydrophilic, hydrophilic, hydrophobic, they alternate throughout the material, and that's a material that we designed a different prototype now with basically layers of MOF to expose more of the MOF and get higher yield. And this was taken by my students in the Mojave Desert. And you see here the humidity measured during the experiment. It rises during this time in October, it rises up to over 50%, but also it goes down during the day as low as almost 7% relative humidity. And the students can still harvest water day and night. Ignore this first column. That's the water that was in the MOF from Berkeley. That's Berkeley water. But this is Mojave Desert water. In this case, we interface the device with a solar panel to allow for power to push air through the material so that we can do more than one cycle, not just day and night, but we can do more than one cycle during the day. So the students harvested 1 liter of water per kilogram of MOF per day under those conditions. And the water is pure, the MOF works very well, and now we have completely electrified the system and made a prototype together with our startup. And you can see there a door opened, air goes in, it goes into a MOF, and then it has cartridges. The MOFs, some MOFs are taking up water, the other MOFs are saturated with water, they are taken out. The water is being taken out by heating. You saw the water collecting at the bottom, and now it's being transferred to a drinking bottle. This device has only 200 grams of MOF. Okay, 200 grams of MOF, and it delivers 5 liters a day. Okay, let me repeat that, 200 liters of MOF and delivers 5 liters a day. So it could easily be in your kitchen. Except I wanted to show you this today. I was gonna have it here, and we resurrected it from our storage, and the students plugged it in, and it ran very well, but then it caught on fire because you're heating the MOF, and since somehow there was no MOF on that cartridge, and the heat basically melted the plastic. So unfortunately, I can't show you that this time. So we wanted to understand. I showed you how water goes into the pores in that MOF. Now I want to show you how the water goes into the MOF, into this MOF. So we have identified every single water molecule in the pores of this MOF by incrementally dosing the material with water. So I'm going to show you this is one pore, and then I'm going to cleave the pore in half, and then I'm going to imagine myself a molecule floating in the pore, and now I can see water in the hydrophilic regions, and now it starts bridging over the hydrophobic regions. And so this push-pull allows you to control the binding energy of the water. That's why you don't need a lot of energy to take the water out of the MOF. So these are my heroes who went to the Death Valley. Ali, you met. Wuchol just graduated. He's a professor in Korea. And Zach, I think many of you met him. He's here. But I thought, well, we should probably have a briefcase size prototype. And so they built this. And inside this device, you have basically pancakes of MOF. And the pancakes are equally spaced to allow air to go in. And it's not electrified. They do this during the night. You saw their picture during the beautiful starry night. During the day, they put it in the sun, and they can harvest water. Okay, you can see now water is bubbling through. Okay, collecting this water. So this is in the Mojave Desert, and the conditions are pretty harsh. I think on that day it was over 120 degrees Fahrenheit, and the humidity was ungodly. I mean, it was below 7% relative humidity. Okay, so what I wanted to say here is that because we have made well-defined materials, we're able to really begin to address major problems. I mentioned carbon capture, but many others with hydrogen storage and others, as well as this water stress. So I think that I'm very optimistic. I'm always optimistic, and I think that this is now being commercialized, and I hope it will make a difference in people's lives. The other thing that we have been doing is doing AI, because the reticular chemistry is very appealing. To AI, you have infinite number of possibilities, infinite number of possible structures, infinite number of applications, and so we've been developing this cycle. And a generous donor donated quite a bit of money. This is Jennifer Shays, who is my colleague in computer science. We teamed up and raised funds for a new institute we call Baker Institute of Digital Materials for the Planet. And the aim here is to develop that interface between data science, machine learning, and high throughput with chemistry and materials. So a result of this AI thinking, machine learning, has been, it didn't give us a good guess, but it certainly gave us a bad guess that allowed us to think in a different way. Okay, so that's another byproduct of AI. The bad guess led us into functionalizing this original linker by adding 2 more carbons. Because the idea was MOF-CO3 is perfect, and I showed you prototypes that work on MOF-CO3. It has perfect adsorptive size, perfect energetics, perfect everything, stability. I mean, this thing has been cycled over 10,000 cycles. No problem. It's stable in water. And now we just want it to have higher capacity. And by adding 2 carbon atoms to that linker, you can increase the capacity by 50%. So now 50% more people in that village could have water to drink. That's the power of reticular chemistry. We call these long arm extension. So this is long arm extension of this linker, LAX. Okay, so to finish, I'm very interested in this problem because it allows us to have distributed mobile off-grid water. You can personalize the water to your taste. It allows you to have pure water that whether you like it or not, you're gonna get pure water, okay? And the exciting thing is that I hope that if we continue to work on this with intensity and with more investments, is that we can achieve water independence to people everywhere. So these are my great students, my heroes, my inspiration. I want to acknowledge their efforts in the lab and also acknowledge that they put up with me. I appreciate that very much. And I want to also acknowledge the financial support and our collaborators. And I want to thank you for staying until the end with me. Thank you very much.